Poke the button and here we go. Quiz yesterday means no homework yesterday. Yay. Everyone got their notebook or whatever you turned in. Okay. Then we just hop right in because no daily quiz or anything like that. Which is good because 1-3 normally is a 2-day lesson. Normally. Since we don't have daily quiz or homework questions, maybe we could get through it. If not, we'll just get as far as we can through 1-3 and continue tomorrow. Just keep rolling. What else? If you're planning on coming down for any reason this afternoon with Spartan time, anything like that, I'm gone this afternoon, so that's not going to happen. If there's anyone who did not do a quiz or needs to make it up, just mornings, I'm always here by 7:30. Staff meeting on Friday, though. I'm always here after school for a good chunk of time. Whether there's loud game club nerds in here or not is debatable. Spartan time and Maroon 2 is my open block. So any time that my door is open and there's not a class, you're welcome to come in and do whatever. So that's that. Here we go. To do continuity, we need to talk about limits. Limits might be a new definition. I know I try to just really quick glance over it when we talk about domain in Algebra 2. I think Mr. Spear does the same. But does anyone remember seeing that kind of notation before? No? Okay. So maybe it was one of those things that for our seniors, if you took an ACT, you might have seen. Okay. Limit is a way to write, as I get really close to this point from both sides, where does it approach on the y's? So as x's go to this spot, what are my y's doing? That's all it is. The limit as I approach this x is what? Think about whoever comes into town from North 85. The limit as I approach that overpass is now 45. And there's usually a cop hanging out there, like tucked behind the hill to speed trap you if you're not. Okay? As I get really close to that sign, I better be going 45. I can do that on a graph. I would say the limit of my function as x is getting really close to 4. Okay, that's how we say this. The limit of my function, so it's just whatever the function name is, g of x, h of x, whatever. As x is approaching 4, so I'm going to come at 4 from the left and the right. So as I get really close to 4, what are my y's doing? No, as I go to 4, not past 4, 4 itself. It gets really close to 5. It might actually touch 5. But as I get close to the 4 button, as I go to 3.9999999, as I go to 4.00001, as close as possible to 4, the y's are going to be as close as possible to 5. So I would just say the limit is 5. That's it. Now, what if I flipped that around and said the limit of my function as x approaches -4? This is what's nice about limits. Okay, so you come at -4 from left and right on the x, and you say, what is my graph doing? Now, there's a hole there. The function doesn't exist. It is not defined at -4. But what is it getting really close to? What are the y's getting really close to? 4. So the limit is still 4. Okay. So think like driving at the Grand Canyon. As I approach the edge, what is my speed? Well, there's no road after the edge, so nothing? No. I'm approaching like 65. Whee! I may not exist after the edge of that canyon, but my speed was still approaching 65. Okay? As I approach -4 from both sides, this is coming up to 3, 3.5, 3.8, 3.9, 3.9999999 on this side, 3.99999, 3.85, 3.5, 3, 3, 3, right? As I come up to the 4, or -4, my y's are getting really close to 4. Even if it doesn't exist there, I can say what it's getting close to. So let's try a couple others. What if I had the limit of my function as x approaches 0? Argue with your neighbors. Okay, remember, as you come at 0 from left and right, where are my y's headed? They don't have to actually exist. They don't have to hit a certain spot, but from left and right, is it going to a specific spot? Okay, I'm hearing a lot say -7. Yeah, and that's exactly it. You go to your x-axis and you say, as I get really, 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 really close to 0, what are my y's doing? Well, they're going to about -7. So that's it. That's my answer. Okay. Now there's different ways that I can look at limit when it goes to end behavior. We'll get to that later, because I can't approach something from the left and the right at the end of a graph if the graph goes to infinity. Okay, so in that case, we have to only approach from one side or the other. There's a notation for it, all that kind of stuff, but this is where we're starting. That is the limit of my function name as x approaches my x value is my y value. And it asks the question, as x approaches this number, what are y's doing? That's what a limit is. As x gets really close to this number, what are the y's doing? Okay? So I might come back to this graph, I don't know. We talk about end behavior. But for now, there's our definition of a limit. Cool? The reason I ask if you'd seen this before, y'all remember like even, odd, positive A, negative A. You might remember a little chart or something like this from Algebra 2 that says if I have an even polynomial, it's going to start and end up at positive infinity. If I have an odd polynomial, it's going to start at negative infinity, go to positive. If I have negative even polynomials, I flip that around. And we would say something like, as x approaches negative infinity, my end behavior is positive infinity. Does that look familiar? Okay. Kind of depends who you had for Algebra 2, I guess. So that's why I was wondering if limits might look a little bit familiar. I know that I do, and I'm pretty sure Spear does, write end behavior like this, trying to get you ready for limits. Because not all kids go on to PreCalc, not all kids go on to college algebra. So if all you see is algebra 2, well, if I at least show you this, then you'll be able to recognize it on an ACT. Instead of what the old Pearson book does, words, they called this a up and down end behavior. That's so dumb. Oh my god. It's like little kid language. Oh, gross. Seaport. Oh, okay. Yeah, don't do that. No, don't do that. Okay. It's just really like childish language. You're big kids. You can handle x approaches infinity. So here's why we need to know limits. Like we start with just a definition, making sure you know limits, because limits are used in, don't hate me, another test. Remember we did symmetry tests? Don't make that noise. Okay. Symmetry tests, continuity tests. To determine if something is continuous, exactly what it sounds like. I can trace the graph by never picking up my pencil through that point. Okay? Now, what I mean by through that point is right here, if I asked when x equals d, is this thing continuous? Well, as I go through the point D, I was able to trace it without picking up my pencil. So yes, it's continuous there. But if I said at x equals c, can I trace through the point C without picking up my pen? No, so it is not continuous. Okay? There's 3 types of discontinuity. That's what this chart is. Infinite. Can we see why it's called infinite discontinuity? Because they go to, the graph will shoot off to infinity, plus or minus. There is, this is the part I want you to add to it, there's a vertical asymptote. Okay, we haven't seen vertical asymptotes since logarithms in Algebra 2. Before that, probably not since rational functions in Algebra 1. It's been a long time. A vertical asymptote is a gap in the domain where it does not exist. I know, you popped up from your seat like a prairie dog.
Thank you.
Huh? There we go. Oh yeah, there's 4 different things rolling around right now. It is really the season for sneezing. You have unchecked spread of COVID because South Dakota. You have RSV, respiratory something virus, is rolling around, especially around little kids. There's a really nasty, almost flu-like 48-hour cold that's rolling around too. My boy just got that. We had to get him tested, and he shrieks bloody murder every time he gets it. Oh yeah, the test is like they get your brain. Okay. And on top of that, it's also fall, so everything is dying and decaying, and there's more pollen and dust and crap in the air. In addition to that whole half of the country is on fire. Yeah, you're gonna have a lot of that stuff. So, anyway, vertical asymptotes. Think about second Hunger Games. Y'all seen the second Hunger Games? They go to the little island. There's a spinning thing in the middle, right? It's like all the victors, right? Okay. If you've seen it, there's a scene in that movie in which They got this like rolling cloud of death fog that's going to come melt her face off. And she falls down the hill, and it's about to come down the hill and melt her, and then it hits this invisible wall. Cannot pass invisible wall. That's a vertical asymptote. It's a point at which the graph literally cannot go through. Now, there are special circumstances where it can go through a horizontal or oblique asymptote. We'll get those in chapter 2. But vertical asymptotes, there's nothing in this class that will go through a vertical asymptote. Okay? So I want you to say vertical asymptote. That's how infinite discontinuity happens. It's a gap in the domain, a place where it literally does not exist. How do I say this one point does not exist? You cannot be here. This guy's not allowed to the party in terms of an equation. What would it look like? X does not equal this. Okay, what types of functions did we have that said X does not equal 2 or 5? We were just doing these the other day. Well, in set builder notation, we said all X is such that X does not equal this or this. What type of problem, what type of function had that? Because that's where we're going to see infinite discontinuity. You're on the right page. You sound like Forky. Okay, you're pointing at the right part. I don't remember what it's called, but there's an X on a denominator. Rational functions. Okay. Algebra fractions. Okay. If you ever have a rational function, which is what this graph is, by the way, or if you want to be Lars, algebra fraction. Okay. An algebra fraction, like this specifically, this graph, this function is f of x equals 1 over x minus c. That's literally what this graph is. Remember transformations? Left, right, up, down. I move bass-backwards land grouped in with x, c to the right. X cannot equal c. So there's a vertical asymptote at c. Okay? That is infinite discontinuity. Infinite discontinuity is the invisible force field wall that your graph cannot go through. So instead it's going to shoot up to infinity or negative infinity. So that's why it's infinite discontinuity. Okay? Jump discontinuity. These are literally when you have to jump from one part of the graph to the other. Besides references of crisscross that you guys won't understand because you weren't born in 1984, these are piecewise functions. Crisscross will make you jump, jump. And a bunch of little 12-year-olds with their pants on backwards, and they had like 28-year-old groupies. Oh yeah. The 90s were wild, y'all. Piecewise functions are when I jump from one rule to another. This would look like f of x is, come on, Frank. And then I would have two different rules. I'd say something like negative 2/3 x minus 5 when x is less than or equal to c. And then I would follow the rule f of x equals x when x is greater than c. Okay? Piecewise functions. We saw these the other day, right? You say which part of the domain am I on? That's the rule I'm going to use. In a piecewise function, I'm going to follow this line all the way until I hit c. Then I'm going to jump to the next rule. I'm going to follow that line instead. And sometimes they're lines, sometimes they're quadratic, sometimes they're absolute value. Who knows? You're going to have all kinds of stuff in there. Okay? But you literally jump from one rule to the other on piecewise functions. That is, jump discontinuity. And finally, come on you, green. Removable discontinuity. This is like Mean Girls of math. This says, all of you are allowed to my party, except you. No, you're cool. You want to come? I'm going to have pizza. It's going to be great. We're going to play a game. We're going to... No, not you. And you single out this one thing is not allowed. But if C is allowed, say that was at 2, isn't 1.999999999 allowed? Isn't 2.000000001 allowed? So I put a circle to show not here. And only not here. These ones, when a single value is removed, this is when I remove a factor. It's been a long time since you've seen these, but what if I had f of x is x plus 2, x minus 3 over, okay. Actually, I should just put c because it's c right here. If we're going to make it accurate, let's make it accurate, right? So here's what I mean by removable factor. We all know that anything over itself is 1. I have x minus c over x minus c. Those cancel out. Factor over factor. I removed a factor. If I were to put in c, so c minus c, 0, like this value, well, that's the one thing that's not allowed. I will never press the C button, or in this case, like 2 or whatever it is. Okay, I'm never going to press that one button. Everything else is good. And that's why what I see as a function is just x plus 2. I just see that line, x plus 2. But there's a hole at C. This one spot is not allowed, open circle. I need you to put a note next to this because most kids don't know this, having not used the calculators enough. Your graphing calculator will not show holes. Pure and simple, a calculator can't show the hole because it's only got so many pixels. How do I put a pixel, a dot, at 2.999999999 and a pixel at 3.000000001, but not at 3? Like, look at that screen. Is that 1080p, ultra 4K, HD? No, That's the screen on that particular calculator is what I was using for my Game Boy Pocket in 1993. Okay? It's not going to be able to show this tiny little hole. And you can zoom in on it. Like, just zoom and zoom and zoom and zoom as far as you can into this point. And I think we started seeing a gap when your window was like less than 10 thousandths of an interval. You finally started seeing a tiny gap, like 1 pixel missing. So you have to know, you can't just look at your calculator screen and say, well, it's continuous because it's a line. See, look. No. Unless you know that removable factors put a hole there, you're not going to see the hole on the screen. You got to know it. Okay? So, the 3 types of discontinuity. The only way that I can prove something is continuous is, yes, a continuity test. Ah, we get to do the whole thing on our calculator. Chill out, okay? Just chill, okay? It's 3 steps, nice and simple. They're going to give me f of x is, and they're going to give me the function rule, and they're going to ask, is it continuous at x is c? They're going to say, is this continuous at this point? Yes or no? So, to run the test, you're going to do 3 things to prove that it's continuous. 1, does f of c exist? Does it even exist? Or does it come back as undefined? Make sure that the C button doesn't break math. You can just go to your calculator, type whatever the function is into y1, go to that ask feature, and just type C. Put in 5. Does this exist at 5? Hit 5, enter. It didn't say error. Yes, it exists. I don't care how ugly it exists. 2, this is why we had to know about limits first. You ask, does the limit of the function as x is getting really close to c exist? I don't even care what it is. I just want to know that it exists. Does the limit exist? Do I get a number? Or do I get it's heading to negative infinity this way and positive infinity that way? Well, those aren't the same number. It's not headed to the same place. So the limit doesn't exist. And finally, speaking of mean girls, right? The limit does not exist. That's where it was a pre-calc joke. Okay. Do those 2 numbers equal each other? Okay. Yeah, Lindsay Lohan, right when she started becoming the raging Hollywood drunk. She used to be such a cute kid too. And then she like got oh yeah, she's a lush. She's bad. No. Yeah, this drunken first period pre-calc. No, like Lindsay Lohan. She is a known alcoholic. Like she comes to Hollywood parties just smashed and like falls on tables. So, but that's it. That's the test. I can do this on my calculator. I plug the function into y1 and then I say, does the C button work? Cool. Okay, let's say C is 2. I would press 2. Does it exist? Yep. I would get really, really close to 2. I'd say 1.999999. Okay, it's this number. 2.00001. Okay, it's this number. Are those numbers the same? Yeah, cool. Then that's my limit. Is that number equal to that number? That's it. That's your test. The solutions for this in the book. Who's actually using the solution manual? The posted solutions that are in Plan Book and Google Drive. Okay? I want you to use those. And I'm going to say it again. If you take any collegiate course, you do a dual credit class next year, you just go on to college classes, you'll put the ISBN number on the back of the book into eBay. Yes, you got to go eBay. Maybe Craigslist, but Craigslist is kind of sketchy. With the words solution manual. Buy that beat up, highlighted, scribbled in piece of junk solution manual from 8 years ago that someone else has used over and over and over. It is worth its weight in gold in any collegiate math class because then you're sure you're doing it right. Okay? It's worth it. And usually you can find them pretty beat up condition for like 20 bucks. Worth its weight in gold. Okay? But the solutions for these in your book, they write out all the tables. They want you to write the tables. Show you that if I'm approaching 2 for my limit, they want you to show -1, 0, 1, 1.5, 1.9, 1.99, 2.01, 2.1, 2.5, 3, 4. So you can see in the table that it's approaching the same thing. Why would I write down the table if I can just have the table in my calculator? Okay? So the solutions are going to have the table written down. You don't have to do that. Just do it in your calculator. Okay? So, example. Right here. I'll run you through the continuity test. If I ask, is f of x continuous at, if I say, is it continuous at x equals 2? I'm going to grab my calculatron. I'm going to clear that out. Actually, I'm going to reset the whole thing because we were doing regression yesterday in Algebra 2. Second plus 7, enter 2. Second plus 7, enter 2. Okay. So first thing, I'm going to take that equation. I'm going to put it into y1. Okay, Frank's still slow. I can write on him, but he's slow. 2 over x. Okay. Alpha y equals brings up the fraction menu on TI-84s. 83s, you just got to use parentheses. Okay. Cool. I'm going to switch my table settings right above window over so I get to just ask my x value, my independent variable. Because now, well, first of all, I'm going to graph it just so I make sure that it is the right graph. It's Frank. Frank is the problem. I did a lesson, because I'm going to be gone this afternoon, I did a lesson video for Algebra 2 on my home laptop and just zoom how fast the emulator works on there. But anyway, there you go. It's the same graph. I know that this is the right equation. Cool. Now that I know it's the right equation, when I go to that table, to run my test, part A, I ask, does the function of 2 exist? I just want to know that if I press the 2 button, does it not break math? Yeah, I got a number. Cool. Next up, oh, back here. Part B, does the limit of my function as x gets really close to 2 exist? This is why the book writes out the table. This is why we just want to use the calculator. I'm going to get really close to 2 from both sides. So I'm going to see at 1.9, 1.99. Oh, come on. I said 1 point. At 1.999. So I'm getting closer and closer and closer. I'm not touching you. I'm not touching you. I'm not touching you. Why are all of these showing up as fractions? Mode. Because I wrote my function as a fraction, and my answers are on auto, I wrote it as a fraction, it'll give me answers as a fraction. If I switch that over to decimal for a little more easy comparison, come on you. You know what, actually, I'm going to come back here, and I'm just going to put in the other one for a comparison side by side. You don't have to do this. You can just switch it over to decimal. -2 divided by x. Okay. See? Okay, so if I write it as a fraction, it gives me a fraction. If I write it as a decimal, it gives me a decimal. So It's getting closer and closer and closer to -1 from this side. Make sure that it still gets closer and closer to -1 from the other side. What if I go to 2.001? What if I go to 2.01? I said point, Frank. What if I go to 2.1? There you go. But you see the same thing? It's as I get closer and closer to 2, other way. Frank's got me all like frazzled here. It's getting closer and closer to that -1 again. So you don't have to do all of these the way that I usually do it. Oh my God, I'm going to break you. Hear an evil electronic voice, not if I break you first. I would put in 2. I would put in, actually, I'd put in really, really close to 2. I'd put in 2 itself. I'd put in really, really close to 2. And I see that it exists. And as I get close to 2 from both sides, it's approaching the same number. So the limit exists. And the limit is -1, because that's where it's headed. Last step, does -1 equal -1? That's it. That's your test. Does it exist? Is it approaching the same limit from both sides? Are those numbers the same? It passed all 3 parts of the test. So I would say f of x is continuous at x equals 2. Because it passed the test. It's slow going at first, but trust me, you can do these problems in like 10 seconds. Try it again. What if I said, is it continuous at x equals 0? I should be able to just look at the graph and say, nah. No, it's not. But, remember back to geometry? Prove this angle is congruent to that angle. Well, friggin' look at them. They're the same. No, you have to prove it. Same thing. First, I'm going to say, does f of 0 exist? You got it in your calculator. Hit the 0 button. Does it work or does it break math? Error. So, does not exist. It's already failed the test, so I know it's not continuous. I'm going to keep going. You got to keep going to show the whole test. Oh, wah. Go f of x as x approaches 0. Go to your calculator and type in -0.001. Get really, really close to 0 from that side. Go to +0.001. Are they headed to the same spot? No, one's headed to positive infinity, the other is headed to negative infinity, which we could see just from the graph. As it approaches 0, they are going to opposite directions. They're not going to the same number. So if it's not going to the same number, then the limit does not exist. Now, ironically, ugly equals ugly. So it actually passed the 3rd part of the test. But I see that it passes this part, but it fails those parts. So it failed the test. It's not continuous. Now I go back up to the top of this slide. Which type of discontinuity was this? Was the infinite, right? There's a vertical asymptote with an x on a denominator. So I would call this infinite discontinuity at x equals 0. The reason I wanted to do this before moving on to the actual examples, we haven't actually even hit example 1 yet. It's a lot of front loading. I'm big on front loading. Do all the talking, do all of the explaining, talk about the thing, and then show you why it works. Because this is a perfect demonstration of a function can be continuous at one spot, but not continuous at another. Can you be functional in one environment, but not another? Right? Like, how many of you are perfectly fine getting up early if it's for thing X? But if it's for school or practice, no. No, I just, no, I don't want to. Okay? So, justify with the continuity test. Determine whether this function is continuous at x equals 2. So one more time, grab the calculatron, type in u. I don't want to reset, deal with everything, okay? What is that, 2x squared minus 3x minus 1? Okay. Go to y equals, come on you. 2x squared minus 3x minus 1. Okay. I do the thing. I switch my table over to ask. God, Frank, you're slow. I go to my table. I want to know, is this continuous at x equals 2, specifically there? So first part of the test, I'm asking, does the function of 2 exist? I press the button, and it says, yup. I ask, does the limit of the function as I get really close to 2 exist? What do I put in? 1.99. Frank, you 0.99. Thank you. And on the other side of it, 2.001. Like, you just got to get close to it. And I see that both of those numbers, as I come at 2 in the middle, they're both headed really close to 1. So that's my limit. And lo and behold, 1 equals 1. So it has passed all 3 parts of my test. I can just say f of x is continuous at x equals 2. That's it. That blue and green stuff, that's all you need to have on your paper for the continuity test. You're doing all the work on the calculator. You're still doing tables. You just don't have to copy them down. So don't get confused if you're looking at the solutions online and they got just tables everywhere. No, we don't play that, okay? Just do it on the calculator, write those parts, and you're good. That's your test, okay? That's all I need from you. So, womp womp. Those. I know that piecewise function is going to look a little iffy if we haven't done them in a long time. Sketch it out. Sketch that function if you don't know whether this is going to be continuous or not. Okay? Run the test. Talk to your neighbors. Argue. Anna, you just missed a perfect opportunity. He asked, where'd you hear that from? You could have been, yo mama. Oh. It would have been perfect because I was walking right by you. The microphone's recording. It would have been great. We would just blah, 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 blah. Yo, mama. Yeah. I'm gonna be 12 for the rest of my life. Deal with it.
It's alright, it's a good way to live.
And my wife's gonna defect to Cambodia or something once my boys are teenagers. 3 of us in the same house.
This one.
Unfortunately, you're gonna have to do 2 different graphs, y1, y2, but you have to ignore one of them on the left side and ignore one of them on the right side. Might be better to just sketch it.
How do you read 1 into the 6? What am I looking at here? That's scientific notation. Okay, so technically it is.
Listen to Mr. Parker. He knows science.
Yes. Thank you. Now you're putting in my head.
Scientific notation. Move the decimal back 6 spaces. Well, back or forward. Depends if it's positive or negative. Oh, hey, look. More COVID stuff.
That seems like such a lie.
The cold is so weird. The cold, so do you have that cold thing? It's so weird.
Yeah, it's,
It's like better than
yeah, which is why you need to get tested. Because one of them sucks. The other sucks and can kill people like me. So. All right, if I'm looking at these as graphs, they shouldn't be long. A cubic looks like this. And just like our parabolas use perfect square steps, over 1, up 1, over 2, up 4, over 3, up 9, perfect squares, a cubic you can graph by using perfect cubes, over 1, up 1, over 2, up 8, over 3, up 27. Y'all got to know these. Okay? Or left 1, down 1, left 2, down 8, left 3, down 27. Okay, so that's how you get your cubic. I'm specifically testing at x equals 0. So I ask the question, does f of 0 exist? If I plug a 0 into x cubed, does it break math or does it give me a number? Oh yeah, 0 cubed is just 0. Yay. Limit of my function as x approaches 0. Okay, on this one, here y'all arguing about it back there, so I'm going to bring it up. Y, clear, I said clear, x to the third, go back to my table. I feel like the sloths from Zootopia. Okay, so I tried 0. Does it work? Uh-huh. I'm going to get really, really close to it on the left. Negative 0.001. What does that mean? 0.000000001. Specifically, negative point, bunch of zeros, 1. Okay, so this is really, really close to 0. And then I say 0.001 on the right side of it, and it says the same thing but positive. So almost 0, negative, almost 0, positive. Looks like they're both headed to 0. So my limit as I approach 0 is indeed 0. Passes second part of the test. Third part of the test, does the function value equal the limit? And sure enough, it does. Don't just do that and quit. Say the word, say the answer. I would say f of x is continuous at x equals 0. Okay. Piecewise graphs, if you don't remember how to actually graph them, if x is less than 0, I'm going to follow this rule. So, what's 1 divided by negative 1? Negative 1, no. What's 1 divided by negative 5? So you'd have like negative 1/2, negative 1/3, negative 1/4, negative 1/5. What if I do 1 divided by negative 1/2? Negative 2, right? Dividing by fractions, easy as pie, flip the second, multiply. So all the way until I hit 0, I'm going to follow that portion of it. There is more to this graph on the other side, but I don't care about it because I only follow this rule before 0. After 0, I'm going to follow just a regular old y equals x. Start at 0, slope of 1. Okay? So that's what the graph looks like. I follow this rule before 0, I follow that rule from 0 and beyond. Now that I have that, run the test. Function of 0. If I put 0 in here, which rule do I use? Equals x. Okay, so plug a 0 in here. I get 0. Hey, cool, it exists. Limit. This one I probably don't want to go to my calculator for, but I can show you how to do it anyway. Think about, as I approach 0 from the left and the right, is it going to the same spot? As I come at it from the left, it's going to negative infinity. As I come at it from the right, it's going to 0. Those two are not the same number. So, the limit does not exist. Because as I come at it from both sides, it's not going to the same spot. One goes to negative infinity, the other goes to 0. Those are not the same. And then finally, 0 does not equal undefined. So it fails that part too. So now you have to say what it is. What type of discontinuity is it when I had a piecewise function that went from this rule to this rule? Crisscross will make you jump, jump. Jump discontinuity at x equals 0. Okay? Seriously, y'all got the chance, like between classes or something, go look up YouTube, crisscross jump. 90s they were something. Nice try, no. I get distracted enough as it is. Okay. So, those were with, like, Frank, you okay? Huh. Those are with just the beginning. I'm going to test at 0. 0 is a nice, easy point to work with. Now we're going to start monkeying around with different types of functions and different types of discontinuity. Piecewise function. Follow this rule from after -3. Follow this rule from -3 onward. So if I'm going to graph that, well, follow this rule all the way up to -3. Which says start here, slope is 3, up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1, down 3, back 1, down 3, back 1. Ooh, we have to go off-road for this. And an open circle. Okay, so I'm following this line from -3 onward. You see why I put the open circle? It doesn't say or equal to. So right after -3, so -2.99999999, from there onward, I will follow this line. Before that, I will follow this line, which we would probably be more comfortable if we wrote it like this. Slope-intercept. Now I'm going to start my line with my intercept, but I'm going to have to erase part of this. Because start at 2 and a slope of -1 says, okay. So that's where the line would be, right? But when do I care about this line? Only from -3 and to the left. So I come to x equals -3. I'm going to start here and follow this line. All the rest of this has to go away. Okay? That's what a piecewise function is. In fact, that's probably the easiest way to make piecewise graphs, is to just graph both and then erase the parts that don't matter. Because I don't know about you, I find it really hard to graph a line in slope-intercept form by not starting at the y-intercept. I find it really hard to graph a parabola if I'm not starting at the vertex. Well, what happens if the vertex is like 7 units away from where I care about it? Right? So, there's my graph. Run the test. They're asking, is it continuous at x equals -3? So, step 1, function of -3. Which rule do I use? Blue or yellow? Oh, I heard a yellow. Why is it blue, not yellow? Or equal to. Okay, so I'll use this rule. I'll plug in a -3, and I get 5. Yay, it exists. I have a friend. Then, limit of my function as x gets really close to -3. So come at -3 from both sides. As I come at -3 from here and here, are they going to the same spot? Not even close. One's going to 5, the other is going to, looks like -11. Those are not the same thing. So since they're not headed to the same place, the limit does not exist. There. And finally, does the function value equal the limit? No. So, if it's discontinuous, identify the type of discontinuity.
Piecewise.
jump discontinuity. Jump discontinuity at x equals -3. This is all I need to see on your paper. You can do the rest on a graph on your calculator. Okay, that's what I need to see. Now, someone's asking, Paul, how do I do this on a calculator? Okay. It's not the greatest because you have to kind of pretend something doesn't exist. 3x minus 2, 2 minus x. They're all sloths? You saying sloth can't be fast? I thought in Zootopia anyone could be anything. I live in Disney hell, y'all. I'm sorry. What was it? 2x minus 3? 3. 3x minus 2. And then 2 minus x. Remember that part. 2 minus x. Okay. Graph-a-fa. How about the weather? Huh?
Trying, man.
Like, come on, Frank. All right. So this line continues down here. If I'm looking at this, now I'm up here. I can do, what is it, 1, 2, 3, there's, I can do one of these numbers. Because, you know, smart boards. Frank does have his uses. Okay? That's the part that I don't care about. But it's really hard to do that on your screen when you can't literally do that. Be nice to my calculators. Dry erase wipes off of screens. Okay? So if you're having trouble with these, you graph the whole thing on your screen, grab a dry erase marker and just like highlight the parts that matter. So you're focused on that. If it helps you, because it just nicely cleans off. Don't use a Sharpie. Okay? I mean, you can get rid of Sharpie. You all know the trick for that, right?
Yes.
Like, this has, was it acetone as one of its compounds? That's why it dry erases. You just Sharpie, go over it with dry erase, and then it wipes off. Okay. So, I think that's why. I think that was one of the parts in the dry erase marker. That's why it works. But anyway, I have this. If I go to my table, you notice now you're going to have both y1 and y2. I'm getting really, really, really close to, we said -3. I have to decide which one do I care about. Which rule was I using? I was using the second rule. Well, hey, look, it exists. Now, if I'm going to get really, really close to it, I have to remember that at -3.001, I'm looking at the blue. Because the blue was everything less than or equal to -3. If I go to -2.99, I have to remember I'm looking at the yellow now. I have to make sure that this number and this number are headed to the same spot. And they're not. Okay? Oh, randomly, something with the new laptops Has anyone watched any of the videos? This isn't inverted on the videos. It was last year. Like, the camera part would look normal. The overlay would look normal, but the board would be inverted like it is in class. Now it's not. So I just realized I said blue and yellow, and that's actually red and blue on the video. So, yeah. So,
So the colors in the stream are normal?
yeah, all of it's normal.
How does that work?
I don't know, because last year the board part was inverted, but because the camera input is its own input feature in the stream software, the camera was always fine. So, I don't know. Someone who knows slobs better than me has got to work with that. But, next one. I've got this. If you want to graph it there, if you want to sketch the graph of it, okay. Yeah, this is all normal right now on the stream. Okay. Well, give it a few movies. Maybe you'll get snapped away, and then you'll have to come back and relearn stuff. When you get back, you'll be fine. You notice that this time they want us to do two different tests. They said test it at -3 and test it at 3. I see a rational function. The first thing that I need to look at, ruh-roh raggy, is what if I factor the denominator? X plus 3x minus 3. So, this cancels with this. So here's what's going to happen. I'm going to see on my screen this. That's what's going to show up on my screen because my calculator doesn't show. I just removed a factor. Calculator doesn't show holes. Okay, so it's going to show this graph with a hole at x equals -3. It's always the 0 of the factor. Okay, prove it. Before I do anything else, I'll come back here. We'll slowly, impatiently erase my values, and then realize I was supposed to be testing it at -3 anyway. For an occasion. Okay. So we'll clear this out. Come down here, clear that out. Come back up here. Okay. Alpha y equals. Come on, Frank. Kill me here, dude. X plus 3 over x squared minus 9. Okay. If I graphify that, how about that weather? There we go. Okay. If I were to trace this, and I said I want to trace it to x equals 3, this is another way you can plug in values. You can just trace them on the screen instead of using the table. At x equals 3, what do I got? Friggin' nothing. Okay, you know what? Let's just do our test right here then. If I'm testing at x equals 3, is it continuous at x equals 3? Function of 3. No. It doesn't exist. The limit of my function as x approaches 3. So maybe I'll trace back to, how about I just poke this? Poke. At 2.87, blah, 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 I see -8.25. If I poke over to the other side of 3, I see 33. Are those headed to the same place? No, one of them's going to negative infinity, the other's going to positive infinity. Those are not the same place, so my limit does not exist. And ugly equals ugly. So at x equals 3, this is not continuous. It failed the test. What type of discontinuity at x equals 3? Infinite. Jump only happens when I have piecewise. Now be careful with piecewise. It's possible that one begins where the other ends. Don't just see a piecewise graph and jump to jump discontinuity. It's possible that one rule ends where the next rule begins. If one ends where the next begins, and that's the point you're testing, technically it is continuous. Because I can, without ever picking up my pencil. Okay? So just be aware of that. That's sort of a gotcha that they do sometimes. I'm going to say this is infinite discontinuity at x equals 3. If I'm testing negative 3, again, I can go to the table or I can just stay right here on the graph. If I trace to negative 3, well, wait, but it's there. It's right there. I said the calculator will not show holes. If I were to zoom in on that point over and over and over, I'd have to make that window really freaking tiny to finally see just a tiny bit of a gap in the line. Okay, so function of negative 3. Does it exist? No. Limit of my function as x approaches negative 3. Okay, I want you to pay close attention here. Look at the y's as I go to negative 3 point blah, 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 blah. As I go to negative, oh. So it looks like on both sides of this, it is actually headed in the same direction. Real quick, I'm going to switch my mode over to decimal so it's a little easier to understand. Not everyone's a fan of fractions. Trace. If I go to negative 3.001, just like I was on my table. If I go to negative 2.999, just like I was on my table. It's headed to negative 0.166666666666666666666. What is that? Shame on all of you. If I have no idea what it is off the top of my head, negative 1 point. So how about that weather? Okay. I'm spamming sixes. So I can go over here and say math. Hey, Frank, turn that into a fraction, please. Yeah. Okay. If you don't know what the fraction is off the top of your head, but it looks like a repeating decimal, head back here, change it into a fraction, please. Now, there's an easier way to do that. Come back here. Wait, did I say 1.6? Oh, you All right, it's 1/6. 0.16666. I put the decimal in the wrong spot. Sorry. It's 1/6. Pretty easy. If I have a hole at negative 3 and I want to know what the function of negative 3 is, or what the limit is, put it in whatever's left. Right? That's what it would have been if there wasn't a hole. Okay? If there wasn't a hole, if this one person, you, isn't allowed to my birthday party, this is what would have happened. Okay? It's a lot easier to just do that. So, my limit does indeed exist. It's negative 1/6. I see over and over and over every year, no matter how hard I stress this, I'll see kids who still just write that as does not exist. No. If there's a removable factor, plug whatever you're testing back into what's left over to find the limit. And then, ugly does not equal negative 1/6, so it still fails a test. It's still discontinuous, but what type of discontinuity is it? No, infinite was at positive 3. What is it at negative 3? It didn't jump from one rule to another. There was no piecewise function. I removed a factor. Removable discontinuity. Okay? If I remove a factor, there's removable discontinuity. In fact, you never even need to see the graph to understand this. The more you do of these, the more you start to just look at this, factor it, and say, oh, well, that's a removable factor. So I'll have removable discontinuity at x equals negative 3. Oh, hey, here's x on a denominator. Thou shalt not divide by 0. This is going to make a vertical asymptote. So there's infinite discontinuity at x equals 3. Right now we're learning the test because you need to be able to justify why you're doing it. When we move forward after this chapter, in fact, even the back half of this chapter, you won't have to do the whole test. You can just look at the function and tell me. Okay? Just like after you proved a bunch of stuff about triangles, you didn't have to do it again. You just used the theorem. Whew! Lot of front loading. Go. Your turn. Those two. The continuity test. Does the function exist? Does the limit exist? Are they the same?
Anyone else? It's like the Eiffel Tower. Yeah. I was not expecting that. Yeah. It works.
My kid ate it hard. Okay, there's a point in parenting where you've told the kid 1,000 times you need to be careful, and then they do the exact same thing that you, yeah, well, not hurt, but he kind of did a big old like cartoon tumble down a dirt pile, and like literally ate dirt, like he was spitting dirt out because he face planted so hard. Learned something, didn't you? Unfortunately, no. But the selfie my wife has of her just trying to contain her laughter and almost in tears is worth it.
Oh,
Hi.
Zero. So no, wait. Okay. Yes.
Okay.
So for this, they're like not approaching 0 because they're getting bigger. When we type in smaller numbers, right?
Yeah,
Right. As you go here and here, So, yeah, 0 doesn't exist, but the limit, as you go to 0 from this side and this side, aren't they both going to infinity?
So it's infinity.
The limit is infinity.
Perfect. Wait, so they are approaching 0.
Yeah, no, they're, as x approaches 0, the y's are both going to infinity. So that is the limit. Now, it's not continuous because there's that invisible force field there.
Yeah. That makes sense now.
And because they go to infinity, that's what makes it infinite discontinuity.
Oh.
It is infinite discontinuity, yeah.
It's this one. But it's just so different.
I might just grab
X equals 2. Should be less than or equal to. So 2 minus 2. Wait, so graph this.
5x equals 4. X can't only be greater than 2.
What are we supposed to be looking for? That?
No. He plugged into this rule, or equal to,
Oh, it's that one.
right? Or equal to. 2 is not greater than 2. You are not taller than yourself. Okay, so as I plug 2 in here, 2 minus 2 is. Okay, so it exists.
Yep.
Now, you need to see as I get, okay, you did put both. Cool.
Yeah, so I was just wondering.
So as you went
what
to 1.99999 on the blue, so this one, it was getting really close to, what's that?
0.00.
Really close to 0. As I went to 2.01, it was getting really, really close to negative 0. Wait a second. Are those going the same place? Let's get some more decimal train on there just in case. Do 1 point spam 9s. Just like you rounded the corner, just keep chucking grenades.
And then run to the other one.
Okay.
Wait, so
Wait, do they both go to 0? As I get really close to 2? As I approach 2, right, is this line going to this line?
No.
No. Hand me dry erase marker behind you. Window, make taller. Let's go up to like 20. So, I'm following the blue line
Yeah.
after 2. So, here.
Yeah.
I'm following red line here. Like, look, they're actually not headed to the same spot. So you can just look at the screen to tell that and say the limit does not exist. Make sure you say the limit of f of x. Okay. I hope we're actually doing this and not just waiting for me to tell you.
you have to put it into the second. Yeah.
The first one.
2 minus 2.
Okay, Kind of like that? So, do the test. Function of 0. If I plug in 0, does it work?
No.
Oh, 1 divided by 0 breaks math law. Already failed the test. But, keep it going. Limit of my function as x approaches 0. If you go into your calculator and you put negative 0.000001, you put a positive 0.000001, aren't they both going to say really Gigantosaurus number? They are both headed to positive infinity. So because they're both headed the same place, it doesn't just have to be a number. Technically, the limit is infinity. They are headed to the same place. They're never going to touch. You know, insert tragic teen romance here. Okay? We're on the same journey, but we'll never meet. And empty set does not equal infinity. So it did fail 2 of them. It did pass 1 of them. The result is still the same. It is not continuous. So I will say, what type of discontinuity? Infinite discontinuity at x equals 0. Okay? This is it. I don't need a whole dissertation for your proof. The test does not need to have a bunch of tables. Just put this. That's all I need. Okay? Contestant 2. If I follow this one, plus 1, 2, 3, 4, x is greater than 2. Oh, wait. That's like 1, 2, 3, 4, 5 over 1. 1, 2, 3, 5 over 1. Ew. That's like this. Right? It's way up there. And then this guy, negative x plus 2. So, look like that. If I'm testing it, it doesn't need to be that hard. I can just look at the graph. The function of 2. Which rule do I put in? Or equal to 2. I'll plug it in here, get 0. Yay, it passes. Limit of my function as x gets really close to 2. Well, I can just eyeball it and say those are not headed to the same place. So the limit does not exist because they're not headed to the same place. And 0 does not equal empty set, contrary to freshman opinion. So, what type of discontinuity jumps from one rule to the other? There you go. Oh, no, we're testing here. Okay. All right. Y'all done good. The assignment should already be on plan book. I will send it out in a few short minutes.